Welcome to our paper on better practices for domain adaptation in the AUTOML 2023 conference. The field of domain adaptation is concerned with learning over distribution shifts. In particular, the common setup is to learn a model on an unlabeled target domain by using a related source domain. Examples of this include adapting a model trained on medical images from one country to images from another country, or a model trained on bread recipes to cake recipes. There are several settings in the literature which differ in what data is available to the model at what time. In unsupervised domain adaptation, the model sees the labeled source and unlabeled target domains simultaneously. In source-free domain adaptation, the model sees only the target domain after potential pre-training on the source. And in test time adaptation, the model sees only a single batch or data point from the target domain at a time and must adapt to it before being evaluated on its predictions. Our goal is to bring domain adaptation closer to the AutoML community by automating the pipeline. Such a pipeline might consist of a dataset or features being fed into an AutoML black box, along with an optimization metric and a compute budget. Inside the black box, we may find hyperparameter or neural architecture search, among other things. The key problem that makes it difficult to realize such an automated pipeline is that in domain adaptation, the model never has access to target domain labels, and therefore we have no validation loss to use as an optimization metric, as we would in a standard supervised setting. So the choice of an optimization metric on unlabeled data is the key problem that we want to tackle in this paper. The optimization metric, or validator as it is often referred to in this setting, is a value computed using some combination of labeled source data if available and the unlabeled target data. There are many potential values that can be computed and used as a validator. For example, we can use the standard validation accuracy as computed on only the labeled source data. We can also use measures like entropy or information, clustering of predictions, distances between the two domains, or measures of feature quality. Many of these have been explored in the literature to some success. Finally, in the academic setting, it is often possible to compute the test accuracy on the target domain by cheating and looking at the test labels. This is unfortunately a practice that has been used in the literature so far. We call this the oracle validator, as it accesses labels that should not be available to the pipeline, and we use it in this work to compare the quality of the other validators. An important recent paper from Musgrave et al. Showed, among other things, that the best available validators are not well correlated with target domain accuracy, and that the differences between algorithms are smaller than the differences between validators. This showed how real progress in domain adaptation was being hampered by the lack of high-quality validators. Building on this, we explore a wider set of validators on multiple domain adaptation settings. Our aim is to determine whether any other validators give consistently strong results such that they could be adopted as the metric in an AutoML pipeline. In order to do this, we perform a large-scale benchmarking study of 11 algorithms and 15 validators across 3 different domain adaptation settings. A lot of work within domain adaptation has relied on manual tuning of hyperparameters. This has led to some overclaims in the literature, and therefore we adopt a more robust and realistic hyperparameter optimization procedure. For each algorithm, we defined a hyperparameter search space that includes the learning rate, the number of epochs, and the weighting of different loss functions. We perform random search and generate 10 hyperparameter samples per algorithm. After saving 20 checkpoints for each training run, we end up with 200 checkpoints per algorithm. Each validator that we will evaluate has access to this pool of 200 checkpoints when selecting the best model according to its score. Now we are ready to move on to the results from our benchmarking study. We start by looking at our results in the UDA setting, where the model has access to the source and target train sets while adapting, an additional source and target val set for validation, and is eventually evaluated on the target test set. This table shows the accuracy of each algorithm and validator pairs, averaged over 21 different domain shifts. The baseline is the source-only model as selected by the source accuracy and corresponds to a model which does not perform any adaptation at all. This achieves 63.48%, and every algorithm validator pair that performs better than this is highlighted in green, while those who perform worse are in red. The validators that select the best performing models in this setting are AMI and vMeasure. followed by the source validation accuracy. And these all come within roughly 3 to 5% of the best possible performance as indicated by the Oracle column. Most validators, however, result in worse performance compared to the no adaptation baseline. We also note that when selecting over source-only model checkpoints, a good candidate can be chosen if using the RankMe or MMD validators. Finally, when looking at the correlation between validator and Oracle scores, we see that the most strongly correlated validator, vMeasure, is still only at 0.65, meaning we have yet to find a validator that accurately matches the test performance. Next, we look at source-free domain adaptation, where the model has access to only the target train set while adapting, an additional target val set for validation, and evaluation on the target test set. In the source-free setting, the situation is a bit different. The baseline sits at 56.49%, and again those who perform better are highlighted in green, those who do worse are in red, but those who achieve less than half of the baseline are now in dark red. This kind of catastrophic failure in adaptation is relatively common in this setting, and it really highlights the importance of choosing the right validator. Because of this potential of destructive adaptation, we tried including the source-only model as part of the pool of checkpoints available to the validators. This did unfortunately not improve the catastrophic cases, and we conclude that there is no simple way of making the adaptation procedure fail-safe. The best performing validator, however, is vMeasure followed by RankMe, and they are again 3 to 5% off the Oracle performance, showing that with the right algorithm validator choice, adaptation can still be successful. However, the correlation values are here much lower, with the largest only being at 0.11. We also note that since the source domain is not available in this setting, the accuracy validator column cannot be computed and is therefore left blank. Our third and final setting is test time adaptation. Here the model adapts on the fly to an incoming batch of target test data, using the same batch for validation before it is evaluated again on that same data. We adopt the episodic version, where after each batch the model is reset and starts adapting from scratch. Our results are perhaps the most surprising in this setting. When we benchmark the algorithms and validators on the artificial dataset CFAR10C, we find that one of the algorithms, TENT, consistently manages to improve upon the baseline, here represented as a dashed line. However, this dataset is constructed by applying artificial corruptions to CFAR10 images. When we instead use a more realistic dataset like Office Home, we find that no TTA algorithm is able to improve on the no adaptation baseline, even with the source-only checkpoint included in the selection pool. These results show that when using a realistic dataset, along with a realistic HPO pipeline, TTA consistently leads to destructive adaptation, meaning the safer choice is to perform no adaptation at all. We can also see that this failure is not solely due to bad validators, since the Oracle validator performance shows little to no improvements either. We now come to the conclusions of our paper. In our large benchmark, we have found that the optimal validator is setting and algorithm dependent. No validator is clearly ready for the AutoML pipeline, unfortunately. But we might recommend, for example, vMeasure for UDA and SFDA, or RankMe for TTA. We have some surprising results in that source only can be competitive with UDA when using RankMe or MMD validators. Validating in SFDA or TTA often fails catastrophically, and we have found no easy way to make it fail-safe. TTA completely fails on more complex distribution shifts, such as Office Home, meaning that sometimes adaptation is actually not worth it.